Okay, so let's just have a look at the second example of the curved surface. So in this example, we have a radial gate like this one, whose face is part of the circle with a radius of the 5 meters. So you can see here 5 meters is the radius of that, kind of like the radial gate. Holds back the water in here. Can you see here? It holds back the water in this section. And the sector of the circle represented by the gate has got an angle of the 30 degrees at its center. So this has got like the 30 degrees at its center. So this is like the sector of the circle has got like the 30 degrees. So the water stands to a depth of 2 meters above the top of the upstream face of the gate. So you can see here the water stands to a depth of the 2 meters above the top of the upstream face of the gate. As you can see, up of the upstream face of the gate is here, and the water surface is 2 meters above that one. The other side of the gate here is the air or atmosphere. So the question here is to calculate the magnitude and the direction of the resultant hydrostatic force here. So here we're just going to calculate for the whole length of the gate, which is 3.5 meters. So we need to calculate not for per meter length, but also for the whole length of the gate, which is 3.5 meters. So let's see how we can just go ahead with that one. So again, we just have two components of the horizontal force and vertical force. So we need to calculate that one. So for horizontal section, we need to calculate we need to first have a vertical projected surface. So this is what we're just going to do. So vertical projected surface, this is this section. So we're just going to calculate here, and we have a distribution of the pressure. You can see it's like a trapezoidal distribution. We need to calculate, identify the center of the pressure, sorry, the centroid. Once we have the centroid, we can just use rho g times the area, and the area is the vertical projected area. And then for FV, you can see the FV, the direction of the FV, by the way, is not like the downside, it's like the upside. You can see here why, because this is like the pressure of the water, vertical one, trying to just push it upside from this direction. However, to calculate the vertical force, we said that we need to just calculate the volume or the weight of the water above that surface. However, if we're just going to look at the vertical or weight above that one, so you can see this area is like for example, the amount of there's no water here, but we can call this area is like a displaced water. So this is the displaced water as something that we can consider as like the vertical weight. Later on, we'll learn this kind of like the vertical displaced water as the buoyancy force. But for now, for the time being, just bear in mind, this kind of like the force is there's no like the real water here, but also it's like a displaced water. Imagine if we don't have this kind of like the gates, this area vertically was full of the water, but this kind of like the area vertical like the area is the displaced water. That is the exact amount of the vertical volume or the weight of the water that we need to calculate, which is equal to the FV. Okay, let's just see how to calculate that one. Maybe for calculating this one, we have a little bit difficulty, because if we're just gonna analyze this one, we can see there's like a rectangular at the top, but there's a sector, part of the sector, this kind of like a 30-degree sector, is going to just be to calculate this section. For example, this section of AED, to calculate that one, the rule is that we know how to calculate the sector, the area of the sector, which is sector of the ACE, to calculate this one. And we have a triangle ADC. Both of them can be calculated. If you take away the area of the ADC from the sector of the ACE, you can easily calculate the remaining section, which is the hatched area in this section. Okay, let's see how we're just going to do this one. So first of all, let's just calculate the horizontal force here. So horizontal force here, we need to just calculate the vertical projected area like this one, so which is equal to the BC. BC, based on the trigonometry. This is like the 30 degree, this is a 60 degree, obviously. So the BC is equal to the hypotenuse 5 times the cosine, which is the adjacent to this, like the 60 degrees, cosine 60. So cosine 60, as you know, is like the half times 5 is 2.5. So BC is easily calculated 2.5. This is our calculations. So if you just look at here again, HG, to calculate the HG is a half of the 2.5 plus 2 meters. So the 2 meters plus half of 2.5 is like a 3.25. So the area can be calculated as the 2.5 times the length. Length is given to us 3.5 meters. Look at that. Look at the problem description. So times 3.5, the area is 8.75 square meter. The area is the vertical projected area. Just pay attention. So we have the area, we have the HG, we can easily calculate the FH, rho G HG A. So rho is 1,000, G is 9.81, HG is like a 3.25 times area is like 8.75 that we calculate here. The result is 278.97 1,000 newtons. Okay, so not per meter because we calculate for the whole 3.5 meters length of the gate. Okay, so that's like the FH. To calculate the FV, just bear in mind, we need to just calculate this kind of like the area, the hatched area. The top one is can be easily calculated, but the bottom one is like a little bit tricky. So let's see how we're just going to calculate this one. So to calculate this one, we need to just first calculate the DE. The DE, how we're just going to calculate the DE? First of all, we need to just calculate the AB. You know, the AB, if you're just going to calculate the AB, you can easily take it away from the 5 meters because 5 meters is the CE. CE minus AB, which is equal to the CD, you can easily calculate the DE. Okay, so see how we can calculate the AB. AB based on the trigonometry from this kind of like a triangle, we say like the hypotenuse 5 times the sine 60 degrees. So sine 60 degrees, which is equal to 4.33 is the AB. So if you're just going to take away AB from the EC, okay, which is 5 meters, which is the radius, okay, 5 meters minus 4.33 is equal to 0.67 meters. So this is the DE. D is calculated here, and we know the DH is like the water from this point to the water surface, like a 2 meters. So you can easily calculate the area of the top section. Okay, so that's like a very simply you can calculate that top section. So we need to just go ahead and calculate the ADE. So the area of the ADE, we need to just have the calculation of the sector. Calculate the sector of the ACE is like the 30 out of 360 degrees of the area of a whole circle. You know, for example, we can just write here 30 divided by 360 means that this section 30 out of 360 times the area of the whole circle, which is pi 5 squared. Okay, 5 squared, that is equal to 6.54 square meters. So this is the area of the sector. This is the area of the sector ACE. So we need to just have the area of the triangle ACD. It's not very difficult. It's like the half of the side times the height. So half times 4.33 times 2.5 is equal to 5.41 square meter. And the area ADE is to just take away 5.45, which is the ACD area that we calculated here, taken away from 6.54. So 6.54 minus, which is the area of the ACE, 6.54. Okay, we calculate here, minus 5.41. The area of the ADE hatch line in this kind of like the part of the sector is equal to 1.13 square meter. So 1.13 square meter plus, so plus the top, like the area of the top rectangular, which is like the 2 meters the height, times 0.67, which is the DE here. So the total area of the hatch area is like a 2.0 47 square meter. So can you see how we just have like how we calculate all of these like the points to just get to this kind of like hashed area? So we have all the area. We need to just multiply by the length, which is a 3.5 meters. So we calculate the volume, which is 8.65 square meters, and substitute in the like the original vertical formula, which is the rho GV 1000 times 9.81 times 8.65. So the total is equal to 84.86 thousand newtons. So that's like the example 2. Oh, sorry, we just have like one more step to go ahead. So just calculate the resultant force. The resultant force, as based on the Pythagoras, we can easily calculate F is, you can just take away the, or factor 1000, you can have like a horizontal force like a 278.97 squared plus vertical force 84.86 squared, all inside the bracket raised to the power 1 second. So the result is like a 291.59 thousand newtons. And the angle phi or phi is like the arctangent FP over FH. FP is like 84.86 divided by 278.97, which is 16, which is equal to 16.9 degrees. So you can just bear in mind that the resultant force is like the working upside. You know, for example, upward. For example, in this direction, you can see here, for example, the horizontal is like very large. You know, for example, horizontal is like the 270. The vertical is much smaller than that. So you can see the angle will be more towards like the horizontal. You know, like the angle is like a 16.9 degrees to the horizontal, passing upward, like in this direction. Let's say if it is in this direction. Okay, so that is the example 2.